Hello everyone, and today's topic is eigenvalues and eigenvectors. In today's video, I'm going to teach you how to find the characteristic polynomial, characteristic equation, eigenvalues, eigenvectors, algebraic multiplicity, and geometric multiplicity of a matrix. See, linear algebra is one of the important topics that comes in CSIR NET. So I'm trying to cover the basics over here because many students have problem in how to find the characteristic polynomial, equation, eigenvalues, eigenvectors. So I hope that through this video I could clear all your doubts. And still, if you have any doubts regarding this topic, then you can ask that through the comment section. So see, an element lambda belonging to F is an eigenvalue of a matrix A belonging to Fn cross n if there exists a non-zero vector x belonging to Fn such that Ax is equals to lambda x. Okay, so here lambda is called the eigenvalue and x is called the eigenvector. And A is the matrix given, okay, of order n cross n. Alright, so now the vector x is said to be the eigenvector of A, corresponding to the eigenvalue lambda. A non-zero row vector y is a left eigenvector of A, that is the matrix A of order n cross n, corresponding to the eigenvalue lambda if ya is equals to lambda y. Now see, for a matrix of order n cross n, the characteristic polynomial of A is given by, this is P of lambda, actually this is lambda, okay, and here also this is also lambda. Okay, so the characteristic polynomial of A is given by PA lambda is equals to determinant of lambda I minus A. Okay, now this can be also written as determinant of A minus lambda I. Okay, both are same. Now next, when we will equate this to 0, that is determinant of A minus lambda I is equals to 0, then this is called the characteristic equation. Okay, now next let us see what is the algebraic multiplicity of lambda. Okay, so the algebraic multiplicity of lambda is the number of times the eigenvalue occurs as a root in the characteristic polynomial of A. Alright, so I will explain all this through an example, but before that let us see what is the geometric multiplicity of a eigenvalue. Okay, now next let us see what is the geometric multiplicity. The geometric multiplicity of an eigenvalue lambda is the dimension of the eigenspace, that is nullity of A minus lambda I. Now let me explain all this through an example. Okay, so question 1, let us take a matrix A is equals to 3 2 0 3. Okay, then find its bit 1 characteristic equation, okay, next eigenvalues, next eigenvectors. Alright, and here we can also find the AM and GM of the eigenvalues. So now let us see the answer. Okay, so the characteristic polynomial bit 1 is given by PA lambda is equals to determinant of A minus lambda I. Okay. And characteristic equation is equals to determinant of A minus lambda I is equals to 0. Alright. So now first let us find A minus lambda I. Okay. So A minus lambda I is equals to 3 0 2 3 minus lambda of I, that is 1 0 0 1. Okay. So we got this as 3 minus lambda 2, and this is 0, and this is 3 minus lambda. Okay. Now let us find determinant of A minus lambda I. Okay. So determinant of A minus lambda I is equals to, see, its determinant, that is determinant of 3 minus lambda 2 0 and 3 minus lambda. Okay. So now let us equate this to 0. See, determinant of A minus lambda I is equals to 0 is the characteristic equation. Okay. So determinant of A minus lambda I is equals to 0. This is actually the characteristic equation. Okay. CH equation. Now this is equals to determinant of 3 minus lambda 2 0 3 minus lambda is equals to 0. So this is equals to, now this implies this is, see, this into this minus this into this. Okay. So this is 3 minus lambda whole square minus 0 is equals to 0. Okay. Now see, this is equals to this 3 minus lambda whole square is equals to 0. This is the characteristic equation of the matrix A. Okay. So this is bit 1. Now bit 2. We need to find the eigenvalues of the matrix A. Okay. So see, this can be written as 3 minus lambda into 3 minus lambda, which is equals to 0. So therefore we got lambda is equals to 3 comma 3. Now these are the eigenvalues of the matrix A. Okay. Next we need to find the eigenvector. Now next we have to find the eigenvectors. Okay. So bit 3, for lambda is equals to 3, the eigenvector is, so how to find the eigenvector? See, according to the definition here, if this is the characteristic polynomial. Okay. Now see here, according to the definition, Ax is equals to lambda x. That means what? A minus lambda I into x is equals to 0. Okay. So from this, here x is the eigenvector, lambda is the eigenvalue, and this is how we will obtain the eigenvector. Okay. By using this equation. So A minus lambda I into x is equals to 0. So here we got A minus lambda I to be how much? See, this one, isn't it? This is A minus lambda I. So this is 3 minus lambda 2 0 3 minus lambda into x. So x, let me write this as x1 x2, and this is equals to 0. Okay. Now we are finding for lambda is equals to 3. Okay. So we will put lambda is equals to 3 over here. So we will get 3 minus 3 is 0, and again this is 2. Now this is 0, and again 3 minus 3 is 0. So see, this into x1 x2 is equals to 0 0. Okay, so here from this, see, this is the second element, that is after multiplying we will get what, 0 into x1 plus 2x2 is equals to 0. This implies 2x2 is equals to 0 or x2 is equals to 0. We got x2 to be 0 but x1 is free here. Okay, x1 is free. So we can take any variable. So let us take k over here. Okay, for x1, then we will get the eigenvector as, then let me represent the eigenvector as capital X. So this is equals to x1 x2. Here we have taken x1 as k and x2 is 0. Okay, so after taking k outside we will get this as like this, 1 comma 0. Okay, so if we take k is equals to 1, see, if k is equals to 1, then the eigenvector is 1 comma 0. You can take any value for k. Okay, so this is one of the eigenvectors of the matrix A, and any multiple of this will also be the eigenvector of A. Okay, so we got the third bit also. This is the third bit, eigenvector of the matrix A. Now see, here we got the eigenvalue as 3, and 3 we got 3 2 times. Okay, so here the algebraic multiplicity of 3 is 2. Am of 3 is equals to 2. Okay, because here the eigenvalues are repeated 2 times. Okay, you can see through the definition also. See, the algebraic multiplicity of lambda is the number of times the eigenvalue occurs as a root in the characteristic polynomial of A. So here from this definition only we got the algebraic multiplicity of 3 to be 2, because this is occurring 2 times. Okay, if it would occur 3 times, then the algebraic multiplicity of 3 would be 3. If 3 would appear 1 time, then the algebraic multiplicity of 3 will be 1. Okay, now let me explain the concept of algebraic multiplicity and geometric multiplicity through an example. So let A be given by 2 3 minus 1, 0 2 minus 1 and 0 0 1. Okay, so here we will find the Am and Gm, that is algebraic multiplicity, and the geometric multiplicity of the eigenvalues, okay, of this matrix. So first we will find the characteristic equation of this matrix, that is determinant of A minus lambda I is equals to 0. Okay, so now this implies determinant, see this much, and this is 2 minus lambda 3 minus 1, 0 2 minus lambda minus 1, 0 0 and 1 minus lambda. Okay, so this is equals to 0. Now this implies I am considering this row. Okay, because for finding determinant you can consider any row or column, just because it will be easy if we consider this row. So that is why I am considering this row, and through this we can find its determinant, that is 1 minus lambda into, see, this is A, this is D. Okay, so AD minus BC. This is how we find its determinant. So therefore this will be 2 minus lambda whole square minus 0, okay, is equals to 0. So otherwise you can just easily remember that see, this is the upper triangular matrix, as you can see from here. See, this is the upper triangular matrix, isn't it? So for a upper triangular matrix, its eigenvalues is equals to the diagonal elements, okay. So here the diagonal elements are what? 2, 2, 1. So see, we will get the eigenvalues as also 1, 2, 2. See, this is 1 minus lambda into 2 minus lambda into 2 minus lambda, okay, which is equals to 0. So therefore lambda is equals to 1 comma 2 comma 2. See, so the eigenvalues are same as that of the diagonal elements, that is 2 to 1. So from here we can see that the algebraic multiplicity of 2 is 2, because 2 is repeated twice, okay, and the algebraic multiplicity of 1 is 1, okay. So see, the algebraic multiplicity of 1 is equals to 1, because it is occurring just once over here, and the algebraic multiplicity of 2 is 2, because it is occurring 2 times. See, 2 comma 2. Now next we will find the GM, that is the geometric multiplicity of lambda is equals to 1, okay. So this is a result that whenever any eigenvalue is occurring just once, then its algebraic multiplicity is going to be equal to its geometric multiplicity, okay. So let me show this by doing it. So for lambda is equals to 1, so GM is equals to the nullity of A minus lambda I, okay. So first we'll find A minus lambda I, okay. So as here lambda is equals to 1, so A minus I, which is equals to, this is 1, 3 minus 1, 0, 1 minus 1, and 0, 0, 0, okay. See, put lambda is equals to 0 over here, okay, then you can get this one. See, when lambda is equals to 1, this is 2 minus 1, 1, then 2 minus 1, again this one is also 1, and 1 minus 1, 0, okay. So this is how we got this one. Next, we got A minus lambda I. Now we have to find what is the nullity of this matrix, okay. So as we can see that here is only one row of zeros, therefore its nullity is 1, okay. So nullity of A minus I is equals to 1, and this is its GM, that is the geometric multiplicity. Now we can see that the geometric multiplicity is equals to the algebraic multiplicity of lambda is equals to 1, okay, for the eigenvalue 1, because 1 is unique, so therefore its AM and GM are equal, okay. So for lambda is equals to 1, AM is equals to GM. Alright, now let us see what we are getting the GM as for lambda is equals to 2, okay. Lambda is repeated 2 times, so its algebraic multiplicity is 2. Now let us find its geometric multiplicity. So see, we will find A minus lambda I, which is equals to A minus, we have taken lambda as 2, minus 2I, okay. So this is equals to, A is this much, 2, 3 minus 1, 0, 2 minus 1, and 0, 0, 1 minus twice of 1 0 0 0 1 0 0 0 1. Okay, so we will get this as 2 minus 2 0, and this is 3 minus 1, this is 0, and this is 0 minus 1, and this is 0 0 1 minus 2 minus 1. Okay, see, so this is what we got. Now we will be seeing, or will be finding its nullity. So the nullity of a minus 2i is how much? See, now we will see whether further it can be reduced or not. So yeah, see, r3 is equals to r3 minus r2. On doing this, we will get this row as 0. See, isn't it? If we add this row to this row, then we will get this as 0. Sorry, subtract. If we subtract the second row from the third row, then we will get the third row as 0. So yeah, this is 0 0 minus 1, and this is 0 3 minus 1. Okay, so this is what we got after reducing. So its nullity is how much? Further, let us check whether further it can be reduced or not. So this row can't be made 0, neither means, yeah, further it can't be reduced to 0. So now the nullity of a minus 2i is equals to 1. Okay, which is not equals to its am, isn't it? Its gm is 1. So therefore its am is not equal to its gm. Fine. For the distinct eigenvalues, its am will always be equal to its gm, but for the eigenvalues occurring more than once, we have to check whether its am is equal to its gm or not. So this was all for today. I'll be explaining the concept of minimal polynomial in the next video. So this was all for today, and thanks for watching. I hope you find these videos helpful. So please hit the subscribe button, and also do not forget to hit the bell icon for getting all the updates of my videos. Thank you.